Hi everybody, this is your 4.2a video on experiments. We're going to do this set of notes in 2 sessions, so you can label today's notes 4.2a and then we'll do 4.2b next time we meet together in class. For this video, it's going to cover the top 4 learning targets in black. We're going to learn about a confounding variable and how it limits our ability to make cause and effect conclusions. We're going to learn about the difference between an observational study and an experiment. We're going to learn some vocabulary with experiments, including experimental units and treatments. And then lastly, we're going to learn a couple different ways to randomly assign people when we are using experiments. Let's go ahead and get started. So to put this in context, in 4.1 we learned about all these different ways to do sample surveys, which are just one type of observational study. Observational studies can give us really good data, but ultimately we can never use an observational study to prove a cause and effect relationship, right? We can use them to demonstrate that 2 variables are related, but not to say one caused the other. That's where experiments are going to come in, okay? The reason we can't use observational studies to prove causation is because of confounding variables. Oftentimes, when we have one explanatory variable and we're using it to see some relationship with the response variable, there are others that could come into play. Take a look at the example at the bottom here. 4,700 children in the Cincinnati Children's Hospital were tested and found that those children whose mothers smoked during their pregnancy were more than twice as likely to develop ADHD as children, as compared to those kids whose moms did not smoke during their pregnancy, right? Now this is an observational study. Sure, they noticed a relationship, those who smoked during pregnancy were almost twice as likely to have children with ADHD, but because it was an observational study, it cannot directly prove cause and effect because, think about it, there are lots of other confounding variables at play here that can affect children after a pregnancy. For example, what was the mom's diet like during her pregnancy? What was the mom's exercise or physical activity like during pregnancy? What's the mother's socioeconomic or employment status? Could she take prenatal vitamins? Could she afford good prenatal care throughout her pregnancy? All of those other factors are confounding variables that might have had an impact on the results. If we wanted to be able to prove cause and effect, we would have to design an experiment where we impose treatments on individuals to measure their responses. Now, sometimes experiments are very practical and help, sometimes they're not. Right? So in the example I just described, it pretty much needed to be an observational study because we know that smoking is not necessarily healthy for pregnant women, so we're not going to design an experiment where we tell 50 women they have to smoke during their pregnancy and 50 women not to, just so we can observe what happens, okay? So sometimes experiments are not practical for health or safety or other reasons, but when they are, experiments can give us a more powerful set of data that we can use to conclude causation. Some questions that might be answered with experiments. Does aspirin reduce the chances of having a heart attack? Can yoga help dogs live longer? Let's take a look at an example to understand the difference between an observational study and an experiment. So here in A and B, we have 2 different scenarios described. Go ahead and read each, and I want you to determine a couple things. What are the explanatory and response variables? And then is each situation either an experiment or an observational study? Pause to do both A and B, and then replay the video when you're ready to hear the answers. So for A, where we had research conducted at the University of Texas comparing people's social media use to their marital status or marital satisfaction, our explanatory variable was how frequently they use social media. The response variable was their marital satisfaction. This was an observational study because we didn't tell people to use social media or not, or how much. Okay? We just observed the behaviors they were already doing and then recorded what happened as the response variable. In part B, the second situation, our explanatory variable is whether or not the people were offered the financial incentives. Everything else stayed the same. Their counseling, weigh-ins, gym pass, but the difference was whether or not they had those financial incentives. The response variable we measured was the amount of weight lost. This is an experiment. We can tell because of our 100 volunteers, they were specifically assigned into two groups where we gave them specific treatments, either the financial incentives or not. Okay? Once you've written down those two examples, one of an observational study, one of an experiment, let's go on to talk about a couple other vocabulary words specific to experiments. So experiments have a couple different vocabulary words that are really particular just to them. The first is treatment, which you've already heard me use. The treatment is the specific condition that we apply to the individuals that we think is going to impact the response. So in the last one, the treatment was either offering the financial incentives or not. We thought that would have some sort of impact on our response variable of weight. Treatments are just different variations of the explanatory variable. So our explanatory variable was whether or not they were offered those financial incentives, and our two treatments were either yes, they were offered those, or no, they weren't. Sometimes in more complex experiments, we could have one where there's multiple different explanatory variables that we're tracking. In that case, we would call those multiple variables factors, and every factor could have different levels or values. We're not going to use the words factor and level quite as often as treatments, but there are a couple questions in the homework where you will put them into practice. The next vocabulary word is experimental units. This is our name for the objects or the individuals to which we are applying our treatments. When the experimental units are people, we often call them subjects. And then our last vocabulary word with experiments is a control group. Often we use a control group for experimental units and assign them no treatment. And then we can use that control group as a baseline for our data when we compare the response variable from the other treatments. I'm going to move this out of the way so you can see the definition here of placebo. So for a placebo, if we don't want people to know that they're in the control group, often we'll give them a placebo, which is just a treatment with no active ingredient. So for example, if we were doing that question, does taking an aspirin help reduce the chances of a heart attack? And we didn't want people to know which group they were in, we might give one group a bottle of aspirin and they take, one every morning and measure the results. We might give the other group still a bottle of pills that look and feel and taste or whatever just like aspirin, but they have no active ingredient in them, okay? Sometimes having a placebo is important to the results because we don't want people to know which group they're in and have their thinking impact the results. Depending on the setup of our experiment, sometimes the placebo is important and sometimes it's not. Let's take a look at another example. Does caffeine affect our pulse rates? A lot of students, and probably most of your teachers, consume caffeine to help them stay awake, stay alert, so it seems possible that this could affect our pulse rates. 50 Tartan High School seniors are randomly assigned to two groups. At the start, everyone's going to measure their pulse rate for 1 minute. Then, one group receives caffeine soda and the other group receives caffeine-free soda. The soda is served in identical plastic cups for each group. 10 minutes later, everyone will measure their pulse rate again and calculate the increase. Pause here while you identify each of the following, and when you're ready to see the answers, you can hit play. So in this case, our explanatory variable is the caffeine consumption. The treatments were either caffeine soda or caffeine-free soda. The response variable we measured is the increase in pulse rate. The experimental units were the 50 Tartan High School seniors. Our control group is the seniors that got caffeine-free soda, and the placebo was the caffeine-free soda. Again, notice that the soda was served in identical plastic cups, so no one knew which group they were in, whether they were getting the caffeine-free soda or the caffeine soda, so that their heart rates or pulse rates wouldn't increase for any other reason, hopefully, other than just the caffeine itself. To finish up today, there are 4 different principles for experiments. The one we just talked about, the example with the caffeine and measuring pulse rates, follows all 4 principles. The first principle is we always want to have groups that we can do a comparison on. Okay? So we are always wanting to design an experiment where we're comparing at least 2 or more treatments. So for example, we had the caffeine group and the caffeine-free group. We wanted to be able to compare them in our measurement of the response variable, pulse rate. The next principle is random assignment. We have to put the experimental units randomly into groups instead of letting people choose, because again, we want to control for those confounding variables. We want to control anything that we can, so any responses we measure are simply due to the explanatory variable alone and not other factors. Third, we want to control. Random assignment is part of how we do that, but we want to, as much as possible, minimize any other potentially confounding variables and keep them the same for all groups. So in the caffeine example, we had people measure their pulse rates for 1 minute at the beginning, 1 minute at the end. We kept them in the same room together. We would want to serve the soda in the exact same cups together, right? So keeping as many other things, as many other variables the same throughout our experiment. And then lastly, replication. We didn't just give 1 senior caffeine soda and 1 senior caffeine-free soda. We split them up and did 25 and 25. We replicated so that we had enough experimental units, enough seniors, that any differences wouldn't be due just to chance alone, right? One person could have a very different pulse rate than another person for a million different reasons. But if we do this experiment and replicate it and have 25 people in our control group and 25 in the caffeine group, then any changes we see aren't just due to changes from one person to one person. Of these, we're going to talk more in detail about comparison, control, and replication in 4.2b, but I'm going to finish today with talking about random assignment, because the way we can randomly assign experimental units is the same way we can do random assignment for sample surveys, which we talked about last time. So random assignment can happen in 3 different ways. The same 3 different ways that we talked about in 4.1. We can use slips of paper, we can use technology like the random number generator on our calculators, or the table of random digits, table D, at the back of our textbook. So if we wanted to take those 50 Tartan High School seniors and randomly assign them into 2 groups, we could do it in any of these 3 ways. If we had slips of paper, right, we need 2 groups, let's call them A and B. We could put A on 25 of the slips of paper and B on the other 25, shuffle them or mix them up, hand one out to each of our 50 Tartan High School seniors. The A students will be in the A group, say that's the caffeine soda group, and the B students will have caffeine-free soda. A simple, easy, and effective way to divide the students into 2 groups. If I wanted to use technology, like the random number generator on my calculator, I could assign every student a number 1 to 50. Then I could randomly generate 25 numbers between 1 and 50 using random integer, random int, 1 up to 50. If I generate 25 numbers, the students with those 25 numbers can be in Group A, and the rest can be in Group B, or vice versa. I could pick 25 people to be in Group B, and everyone else is in Group A. Similarly, using the table of random digits at the back of our textbook, I could assign every student a 2-digit number, right, because I have to get up to 50, which is a 2-digit number. So I could assign them a 2-digit number from 1 up to 50. Then I could go to a random line in Table D at the back of my textbook and start reading 2-digit groups of number from left to right. As I do that, the students with the first 25 numbers chosen will have caffeine soda, and the rest will have caffeine-free soda. Notice that there are 2-digit numbers beyond 01 to 50, so if I get a number from 51 to 99, I'm going to need to ignore it. I'm also going to need to ignore any repeats or duplicates. So for example, if I already chose person 16 and I come to another 16 in the line, I'm going to have to ignore the second 16. I can't choose the same person, the same student, twice. So this ends your 4.2a notes on experiments. At the end of this, you should know the difference between an experiment and an observational study. You should know that we can use experiments to prove cause and effect. Studies cannot prove cause and effect because of the confounding variables. You should know some of the vocabulary associated with experiments, including treatments, experimental units, and control groups, as well as the 4 principles of experiments, including replication, control, random assignment, and comparison. Go ahead and start the 4.2a homework, and I'll see you in class next time.